Hi, my name is Sahil Jain. I'm a junior at Princeton studying computer science, and I've been working with Professor Skovsky this semester on my project, an implicit deep learning based approach towards zero-shot learning. So, memory is one of the biggest challenges in deep neural networks today. Memory in neural networks is required to store input data, weight parameters, and activations as input propagates through the network. In fact, it must be retained until they can be used to calculate the error gradients in the backwards pass. Commonly known, the 50-layer ResNet network has 26 million weight parameters and computes 16 million activations in the forward pass. In fact, at Microsoft, 8.8% of job failures were caused by the exhaustion of GPU memory, which accounts for the single largest category in all deep learning specific failures. So it's clear that GPU memory utilization is a big problem today. And to solve this, we're going to use something called implicit deep learning. It's a relatively old concept, been around since 1980, but only recently have researchers at CMU begun to explore its use towards modern-day machine learning tasks, from computer vision to sequence models, given the expansive auto-diff tools that we have available today. With implicit deep learning, Bai et al. At CMU show up to an 88% reduction in GPU memory utilization for common computer vision tasks. Additionally, implicit layers are easy and elegant in terms of their implementation, given that they consist of only a single layer. Previously, Bai et al. Investigated the performance of deep equilibrium models on object classification tasks, namely ImageNet and CFAR, and also semantic segmentation on the Cityscapes dataset. The goal of this project is to apply implicit deep learning to zero-shot learning. It's interesting in particular to apply this to zero-shot learning because the problem setup is such that at test time, a learner observes samples from classes which were not observed during training and needs to predict the class that they belong to. It's an interesting challenge because we are able to truly test the ability of the implicit neural network to capture features, and in this case, especially important because of how different the train and the test datasets are. So how is explicit deep learning different from implicit? In explicit, we have multiple layers with a specified model architecture. Namely, given some input x, compute y using the function f. Typically, we provide a forward computation graph for the forward pass and backprop through that computation graph to compute as we compute the gradients. In implicit deep learning, it's a little different. It's only one layer, and we are seeking to satisfy some joint condition on the input and output. So given some function x, or some function g, and an input x, find a y such that that function is equal to 0. We see this a lot in things like fixed point iteration, optimization problems, differential equations, etc. And their use is largely motivated by the key observation that hidden layers of many deep sequence models end up converging towards some fixed point. And so having multiple layers doesn't really do too much for us. And so the model on the left is the model architecture that we're using in this case. Now, we use two key observations here. The first is that we use something called weight tying. In weight tying, we say, apply the same weight matrix to every layer in the model. And I know this may seem a little weird, but it's actually way more common in machine learning than you might think. And what we can notice is that once we keep applying the same weight matrix to some input x and the consequent vector z, eventually we're going to converge to some fixed point. And if we end up actually just converging to this fixed point, does it make sense to have a bunch of these weight matrices that essentially end up doing nothing? Instead, we can represent this network using a deep equilibrium model, which is a single layer that computes this fixed point. So for some input x and a weight matrix w, compute the fixed point such that any number of weight matrices applied to this input would result in the same vector z. And we can solve for this using a fixed point solver. In this case, we use Broyden's method, but there's a lot of interesting tools out there for this purpose. Now, what is the math behind deep equilibrium models? So in the forward pass, as aforementioned, we compute some equilibrium point z star, where z star is equal to the function f of z star and the input x. We'll compute loss as a function of z star as well. Now, more interestingly, in the backpropagation, we are able to use the implicit function theorem to directly compute gradients. Now, note that in this gradient, we do have to compute a Jacobian, but this can be done optimally using modern-day auto-diff tools. The key observation here is that because there's only one layer and we can compute the gradients directly, we don't need to backprop over multiple layers. We don't need to store all of the intermediate values as we backprop from beginning to end because there's only one layer and there's a very simple formula to calculate that gradient. So what work has been done on implicit deep learning in the past? Coulter and collaborators showed success of their implicit framework, namely deep equilibrium models for the task of sequence modeling. We'll be using that in this case as well. Chen has shown implicit models to construct a related class of models, namely neural ordinary differential equations, which are used for more complex problems in fields like physics. Zhang and co-authors have shown the usefulness of this kind of implicit rule in the context of recurrent neural networks. And they actually help solve some of the long-standing issues in training RNNs. Also, there's just generally work being done in implicit neural networks, but nothing has been done for zero-shot learning, and I'm excited to show you some of the results I've come up with. So briefly, the data set that we use has 30,000 images. The animals with attributes data set, there's 50 animal classes, 40 for training and 10 for testing, roughly 85% to 15% split. I've designed the network such that the training task is to predict these 85 feature attribute vectors. We use the predicted attribute vectors to find the nearest attribute vector that exists for our training and test classes and assign an animal class based on the predicted vector and the training and test vectors by computing the Euclidean distance and taking the minimum distance vector there. So to compare apples to apples, I first trained an explicit network using the VGG19 traditional architecture. This architecture is pre-trained with ImageNet weights where we retrain the last 3 layers, adding a dense layer, a dropout layer, and another dense layer. The results were actually pretty good. The hyperparameters as shown in this slide, which I won't go over, but in terms of predicting raw attributes, it was able to predict 90% of the attributes on the training data set and 74% of attributes on the test data set. These are images it's never seen before, so that's actually very impressive. For predicting animals on the predicted attribute vectors, it was able to predict 85% of the animals correctly on the training data set and 43% of the animals in the test data set. So definitely performing super highly here and not state of the art, but a good comparison for our deep equilibrium model. So next I can discuss the deep equilibrium model design as shown here. I chose this design because it's a very typical design for residual cells, which have worked very well when used in traditional explicit deep learning tasks. In this case, we solve for z star at every iteration given the input x as shown here, and during backprop, all of the weight vectors in this network are updated. The deep equilibrium model was also trained with similar hyperparameters to the VGG19 network to maintain consistency. While the DEQ did not outperform the VGG19 network, its performance was very close. The attribute prediction accuracies were only 3% off, and the animal class prediction accuracies were approximately 10% off as well. However, more interestingly, I used NVIDIA SMI to track the GPU memory usage for both models, and the DEQ ended up using 20% less memory than the VGG19 model. The number of parameters in both cases were within 10% of each other and negligible in terms of their differences. So there's a number of challenges I faced with training the DEQ, given that this is a relatively unexplored field. With only a few research groups working on it, the DEQ codebase is quite difficult to parse, and future work could involve developing abstractions to make it easier to use. Furthermore, the DEQ model trains slower due to the fixed point iteration happening, and took hours to train despite a small batch size and also training on a Tesla P100 GPU. In order to improve the DEQ performance, I ended up using the original image size of 128 by 3 rather than 32 by 32, tuned hyperparameters, which ended up being a time-consuming process, and also fiddled with the DEQ model design and updated some of the parameter counts there as well. There's a lot of analysis that I couldn't get to in this talk, but will be explained in the paper, namely confusion matrices, memory utilization analysis, and comparisons on the per attribute performance to uncover the black box behind both models and also offer some observability into DEQs. More importantly, it's exciting that we were able to replicate similar results to a VGG19 network with DEQs on a CV task that hasn't been applied to implicit neural networks before. I can't wait to keep going at this and share more of my results in the paper. Thank you.